is quantum symmetric pairs, part 1, please.
Okay. Well, first of all, I'd like to thank the organizers for the most generous invitation. I'm very grateful to be here, and it's certainly an honor to talk for Professor Okado's birthday conference. So this is actually my second time in Osaka. The first time is more than 20 years ago. And usually when something is that long in the past, I don't remember when exactly it was, or maybe not even the year. But in that case, I do remember, because the first time I arrived in Osaka was at September 11, 2001. And that was certainly a dramatic visit. And so I was very pleased to get on the plane this time and just arrived in Japan. And the world was the same as it was when I entered the plane. So I want to tell you a little bit about quantum symmetric pairs. And quantum symmetric pairs actually also have a connection to the Kansai region. They also have an anniversary, if you want. They were invented, I would say, proper 30 years ago, about 1993, by Professor Nomi in Kobe, when he wrote the preprint version of his first paper on quantum symmetric pairs of type A1 and A2. So this is SLN, SON inside SLN, and SP2N inside SL2N. Now, Professor Nomi took an FRT approach to quantum symmetric pairs, and the talk today and the following talks are more about Gay-Letzter's approach, who took a Greenfeld-Jimbo approach to these algebras. Now, you know, for quantum groups, the FRT approach, the starting point is a solution of the quantum Young-Baxter equation. And then you use this to define the quantum algebra. So you do see the quantum Young-Baxter equation at the very start of the defining your algebras. Now, the same is true in Professor Nomi's approach. You see the quantum reflection equation at the very beginning of his defining these algebras. On the other hand, in the Greenfeld-Jimbo approach, you don't see the quantum Young-Baxter equation at the very beginning. You have to work a little bit for it to. You have to work a little bit to get this quantum solutions to the quantum Young-Baxter equation. And so the same is true with Gay-Letzter's approach to quantum symmetric pairs, which I want to talk about. And so what I want to tell you then is where this quantum solutions to this quantum reflection equation or universal K matrix, where they sit in her approach. So my plan is for today to give you an elementary introduction to quantum symmetric pairs. I know there are some experts in the room. They will have to bear with me. And then in the second talk, I want to tell you about a so-called star product realization of these quantum symmetric pairs. That is something we've been using in joint work with Milan Yakimov over the past couple of years. And that turned out, in my view, to be quite an efficient view to look at these algebras. And then in the third talk, I want to tell you more about these universal K matrices and how to find them. This is ongoing work. There has been progress even over the last couple of years and months, not by me, but by other people. But one sees that the theory just keeps developing. Okay, so now an introduction to quantum symmetric pairs. So what do? We start with the symmetrizable Hertz-Moody algebra. And then we have an involutive automorphism of this, theta. So involutive meaning that theta squared is the identity. And so then our G decomposes into the +1 and the -1 eigenspace. And the +1 eigenspace is a Lie subalgebra of G, and therefore the universal enveloping algebra of K is a Hopf subalgebra of the universal enveloping algebra of G. And so then even if this is finite dimensional and both of them are, say, simple, if you go to Greenfeld-Jimbo quantum groups, then there is usually no way of seeing one of these inside the other. So the goal of the theory as formulated by Gay-Letzter is to find a different quantization, find a subalgebra UQ of K prime inside UQ of G, a subalgebra, such that the following two properties hold. So it's too much to ask that this subalgebra is a Hopf subalgebra. We have a weaker property that it's a one-sided coideal subalgebra. So I need a little bit of notation here. UQ of G is, let's work over a field of rational functions in a variable Q in generators EI, FI, and KI to the plus minus 1 for I in some index set I. And then mod some relations which are not so important at the moment. But what is important is the form of the coproduct. So just to fix conventions, so we have delta of EI is EI tensor 1 plus KI tensor EI, and delta of FI is FI tensor KI to the minus 1 plus 1 tensor FI. So that's the conventions I want to work with. Okay, so the delta is my coproduct. And so we want the delta of UQ prime of K. Well, it's not a Hopf algebra, but it's a right coideal subalgebra. So this is contained in UQ prime of K, tensor UQ of G. And the second property is that we want that if in a sensible way we let Q go to 1, then we want to get U of K back. Yeah, so for Q to 1, and this is made precise by non-restricted specialization. Okay, so that is the goal. And so here's our first example. So we take G equal to SLN, and theta, the involution, theta of X is minus X transpose. Then the fixed Lie subalgebra K is SON. Okay, so SON is generated as a Lie algebra. That's the skew symmetric matrices by Fi minus EI, I from 1 to n minus 1. So these are the Chevrolet generators. Now I want a quantum version of this, UQ prime of K. Well, I would be tempted to define this as the subalgebra generated by Fi minus EI. Yeah, but this doesn't work because of my convention for the coproduct. So if I want the coproduct property, then I have to make sure that these two elements somehow have similar coproducts. And I get this by multiplying here by a Ki to the minus 1. But then you will say, well, that's a bit random. You could have written the Ki to the minus 1 to the other side, and you would have gotten a factor, and you would have gotten something different. So I will allow for this. I will allow for factor Ci. So this is my set I in this case, where the factor Ci is just a scalar. And so Ci is an element in KQ. And I write bold C for the set of all these Ci. And so then my algebra suddenly depends on these parameters. So I will also call it curly B C. And these elements here I will call BI. And then you see that the way I've built it up, well, the co-product of the Fi and this Ei Ki to the -1, they're exactly of the same form. So we get the delta of Bi is equal to Bi tensor Ki to the -1 plus 1 tensor Bi. And the first entry is always in my subalgebra. And so this is in BC tensor UQG, and therefore it's the right co-ideal. And moreover, if I choose these coefficients such that for Q equal to 1, they are equal to 1, then you'll believe me that this indisputable notion of specialization goes to U of K for Q going to 1. Okay, so that's our first example. But now we want to do this in large generality for essentially any automorphism of a symmetrizable Kac-Moody algebra, or at least half of them. And so for this, we need to look at Satake diagrams. So the nice thing is that involutive automorphisms of G are parametrized by these Satake diagrams. So what is this? So we have X pairs X and tau, where X is a subset of my set of nodes of the Dinkin diagram, and tau is a diagram automorphism, which moreover maps X to itself. And then there are some properties. So tau squared is the identity. Secondly, if I restrict tau to X, then I want this to be the longest element in the parabolic subgroup of the Weyl group corresponding to X. So I forgot to say that X needs to be a finite type. So what does this equation mean? That means that minus Wx of alpha I is equal to alpha tau of I for all I in X. And then thirdly, there is this condition if J is not in X and tau of J is J, then alpha J evaluated on the half sum of the positive co-roots corresponding to X has to be an integer. Okay, so that is the Satake diagrams. And now we can look at some examples. So for G equal to SL4, well, I have two possibilities. So tau can be the identity. If tau is the identity, well, then I always have the Dinkin diagram itself. So I should say that I meant to do an example. So we notate this typically by painting the nodes in X black, and black is now white. and by indicating the diagram automorphism like so. Yeah, so I always have the case where X is the empty set. Yeah, then what I cannot do is just have one of these nodes black, because if I put just one of them black, like this one, then the alpha 2 evaluated on the H1 here on the half sum of positive co-roots is -1/2. But what I can do is this. And that is essentially it when tau is the identity. And then tau can be unequal to the identity. And then again, I can take this one where everything is white, like so. So here again, X is the empty set. And then what I cannot do is take, right, I want to set X, which is invariant under my diagram automorphism. I cannot take the two outer vertices because of this condition here, but I can take this inner vertex, like so. Okay, so that's the Satake diagrams. And then the good news is that they classify involutive automorphisms in some sense. So we need a little bit of notation. We need the Chevalier involution. Omega. So on the Chevalier generators, omega of EI. So I follow Cutts notation here, and we put a minus sign in front of those. That's not really essential. And omega on the Cartan subalgebra is minus the identity. And so then if you give me such a Satake diagram, how do I get my involutive automorphism? Well, if there is no black dots, then I just take the Chevalier involution. If tau is the identity, if tau is not the identity, then I compose with tau. If there are black dots, then I take the longest element in the Weil group, Wx. So the Weil group gives us an action of the corresponding braid group by automorphisms on G, and I just take this action for this longest element, Wx. Yeah, so, okay, so I write a decomposition of this Wx in terms of simple reflections, and then at Si is given by triple exponential x of at EI, x of at minus Fi, x of at EI. And so this is a very good map. If you look at this and you square it, well, this is an automorphism of G. If you square it, it's nearly the identity up to a sign on certain root spaces. It is the identity on the simple or semi-simple Lie subalgebra corresponding to X. But on some other root spaces, it may be a sign. It may be a -1. And so we don't want this. And so you have to put some fudge factor here, out of S. So this is just an automorphism, which is a sign on some root spaces and the identity on others. And I don't want to go into detail for that, but that's how we get an automorphism. And then the theorem due to Cutts and SP1 from 92 says this is a bijection. This is a bijection. Well, between what? So on the left side, we have the Satake diagrams up to, well, I can act on the Satake diagrams by diagram automorphisms of I. So up to action of the diagram automorphisms, And on the right-hand side, we have involutive automorphisms of G, and these involutive automorphisms are of the so-called second kind. So what does that mean? Well, if you look at your omega here, then this flips the positive Borel into the negative Borel. The diagram automorphism doesn't do anything. Then, because X is a finite type, this longest element will flip finitely many root spaces back up again. But all but finitely many root spaces will be mapped from the positive Borel into the negative Borel. And this thing doesn't do anything. Yeah, so of the second kind means that we get involutions which flip the positive Borel into a negative one, and up to something finite dimensional. So the kind of involutions we don't get are those which are just given by an involutive diagram automorphisms. Yeah, there's no way quantum symmetric pairs, we don't have a theory of quantum symmetric pairs for these kind of involutions. Okay, I want to make one remark here, which is not relevant for this theorem, but is relevant for the theory of quantum symmetric pairs. And this is an observation by Rogalskis and Blah from 2020. And they tell us that we can replace property 3 of a Satake diagram by something somewhat simpler, 3 prime, which says that x tau, the Satake diagram, does not contain a rank 1 component of the following form, and this is now very easy. So type A2 with one black node and one white node. Yeah, it's clear that in our Satake diagram, this is not allowed because this condition wouldn't be fulfilled. But what they say is that if you want to build a good theory of quantum symmetric pairs, then you can actually look at all diagrams which have satisfy conditions 1, 2, and this simplified condition 3 prime. Yeah, and the reason this works, well, these are still good classes. So in the finite type, there is a paper from the 80s by a person called Heck, and he proves, among other things, that if you look at these diagrams, then so you have involutions corresponding to this. You have involutions Wx composed with tau on the Katang subalgebra, and so that allows you to introduce notions of restricted root systems. Yeah, you just take your root system, you look at the -1 eigenspace of this involution, and you restrict to that. So that would be one definition of a restricted root system. But there's, and then there's a corresponding Weil group. But on the other hand, you can look at this. This gives you an involution on the Weil group, and you can look at the fixed subgroup, and then you can divide by the part of Wx. Yeah, so you always have the Weil group corresponding to X inside of your Weil group. So you look at the invariance. Wx is a subgroup of that. You divide that out. That is also a candidate for the restricted Weil group of the restricted root system. And the statement is that, well, if you replace 3 by 3 prime, then these two definitions are the same. And there are many other desirable properties. Yeah, so quantum symmetric pairs can be built with these slightly more general diagrams. Yeah, and you get, for example, in type B, you get an extra diagram, even in finite type. So this is Satake, a Satake diagram, but this one is not. Yeah, but it doesn't have a component of this type, so that would be allowed. And so there's quantum symmetric pairs in this setting as well.
What do you mean by component? So,
right, yeah, it's a good question. So I take a Satake diagram, I take a white node, and I take all the black nodes. And then I take a connected component of the single white node I have singled out and all the black nodes which are connected to it. And that's a rank 1 subdiagram. That'll always satisfy these properties as well. Yeah, so the rank is the number of white nodes in a diagram. Okay? So this is rank 1. This is not rank 1. This is rank 2. So it would be the orbits, number of orbits of white nodes. Yeah, this is rank 1. So it doesn't have a component of type. So this one, right? You take the your one node, you take its orbit. I should have said you take its orbit and all the black nodes which are connected to it. So you get 2 black nodes, and so it doesn't have a component of this form. Okay. Okay, so now we want to define these quantum symmetric pair algebras. And we first look at the classical case. So from now on, always theta is the involution given by a Satake diagram like so. Like up there. And so what is, in this case, the Lie subalgebra K generated by? So firstly, my involution restricted to the semi-simple Lie subalgebra corresponding to X will be the identity. That's how it's cooked up. So this lies in K. Then certainly what lies in K, well, is K intersected with the Cartan subalgebra. And then thirdly, just as in the SON example, well, we get elements of the form Fi plus theta of Fi. And I can write this out. So this is Fi plus at Wx E tau of I. And I get a minus sign. And then there is the fudge factor, which I wanted to suppress. So here's my at S, maybe another sign. Okay, so that is what K is generated by. And so we now get a quantum analog of this just by taking quantum group analogs of these 3 kinds of generators. So this is the definition given by Gay-Letzter. In 1999. So UQ prime of K is the subalgebra of UQG generated by the following 3 components. So I denote by curly mx the UQ of GX as a subalgebra of UQG. Then we want U0 theta. So this is the subalgebra generated by Ki K tau of I to the -1 and Kj to the ±1, where I is not an X and J is an X. So I can reformulate this. So if I take if I write Q theta as the elements mu in the root lattice, such that Wx tau of mu is minus mu, or minus Wx tau of mu is mu, then this is just the group algebra of this subgroup of the root lattice. And then thirdly, we have analogs of these things, and we do this in exactly the same way as we did this for SON. So we take Fi minus, so now the E tau of I becomes the E tau of I. And then I need an analog of this at Wx, but there is a braid group action by automorphisms on UQG. These are called the Lustig automorphisms, and there is one for each element in the Weil group, and they satisfy braid relations. And so we apply this thing to E tau of I, and that gives us an analog of this. And so I've suppressed the fudge factor because, as before, I want to allow an arbitrary factor. Again, to make this a co-ideal, I need a ki to the minus 1 here. But then I allow an arbitrary factor, ci. So ci is still a scalar. And then I call these elements bi. And these are my generators. And again, the algebra then depends on the family of parameters, which I fix, and I write a vector C here for all these numbers. And that is our co-ideal subalgebra. Okay, so now we have two things to check here. The first, we had two conditions. We want our subalgebra to be a co-ideal, and we want it for Q going to 1. We want this to go to U of K. So that's the two things we have to check. The co-ideal property, well, this is a Hopf subalgebra, this is a Hopf subalgebra, so one only has to look at this element. And for this element, one can do this the pedestrian way. I want to show you a slightly more sophisticated way of showing the co-ideal property for this element. So the point is that these Lustig automorphisms, they are actually initially not defined on UQ of G, but they are defined on integrable weight modules. And if I think of all of UQ of G being defined by their actions on integrable weight modules, well, then I can write this definition as elements acting on integrable weight modules, and then this TWX becomes a conjugation. Yeah, so I can write my BI as Fi minus Ci TWX, but now this TWX is the action on the weight modules, E tau of I, TWX to the minus 1 times Ki to the minus 1. Okay, so now this TWX, we know the co-product of this, and this is given in terms of the so-called quasi-R matrix. So what is the quasi-R matrix? So I write a capital theta, not to be confused with our involution, which only has one line. This is a capital theta corresponding to X. So this has various descriptions, but we can write it down as a sum of dual bases. So we have a non-degenerate pairing between we have a skew-Hopf pairing between the positive and the negative Borel for this UQ of GX. And this restricts to a non-degenerate pairing of the negative part and the positive part. And so we take sums of dual bases, and I write this as F, maybe X mu tensor E X mu. maybe you need a sign, -1 to the height of mu. And the mu runs over the positive cone of Qx. Okay, and it's an infinite sum, so really it's a product. So it's an element in the product, mu element Qx plus of u minus mu minus tensor u plus mu. So these are the weight spaces of u. U is UQG. UQG. And u minus is the subalgebra generated by the F's and u plus by the E's. Okay, so there's this canonical element, but the point is that this canonical element can be expressed in terms of these braid operators. We can write this as delta TWX to the -1 composed with TWX tensor TWX. Okay, so that's a formula which, well, for just one simple reflection one finds in the very early parts of Lustig's book, and later on, I think, also for finite type longest elements. And so now we can use this. So from this, we get the delta of TWX is TWX tensor TWX times this theta x. And so now we can just plug this into the coproduct of the BI. So we get that delta of BI is, well, it's delta of F, Fi tensor Ki to the -1 plus 1 tensor Fi minus Ci, and now I have to, well, I have to plug this in. So TWX tensor TWX composed with this was a theta to the -1, theta x to the -1, then delta of E tau of I tensor 1 plus K tau of I, E tau of I.
So sorry, I have a question. TW is somehow infinite sum?
That's an infinite sum, yes.
Yeah. So you may, I think you use completion of some.
Right. So I look at these. This is true. So I look at these as operators in integrable highest weight modules.
I'm confusing. Theta is some tensor. Right hand, left is F and right is E. So
yes,
I mean left is somehow this direction and right is this direction.
Yes. So
which completion? Yeah.
So I don't care about a formal completion. I just say, because I only look at highest weight modules, this sum will act finite on any tensor product.
So you only see right side.
The right side will terminate, and then the left side has nowhere to go because its partner is gone. Yes.
Okay.
Yes. Okay. So right, let's finish that. So we have theta x TWX to the -1 tensor TWX to the -1, and then delta of K of I. So we have a Ki to the -1 tensor Ki to the -1. And now the point is the following, that we have here this term, E tau of I tensor 1. We have this theta x, which has the F's in Gx in the first entry, and those F's in Gx commute with the E tau of I, because the I was not in X. Yeah, so these are the UQG relations. And that means if I only look at the first term, I can pull this theta X past. It will eat itself up. And then I just have the conjugation by the TWX. Well, that gives me my old Lustig action on E tau of I. And on the one, it doesn't do anything. And so what I get is corresponding to this Fi, the rest which I need from my generator, exactly this element. Yeah, so I can write that this is equal to Bi tensor Ki to the minus 1 plus 1 tensor Fi. And so that is this. And then I only have this second term left. And if we stare at the second term, I forgot to tensor here. Yeah, we bring this Ki to the minus 1 past the TWX. Then we get here something which lies in U0 theta in the first tensor entry. Yeah, then we conjugate by this. Well, this just gives us something which lies in mx U0 theta. And then we apply the TWX. That doesn't change it either. Yeah, so the term which comes from here lies in, I can maybe write mx U0 theta tensor U Q of G. And then it's not an equality, but it's an element in this set. Yeah, so we get that the coproduct of Bi looks like this. Bi tensor Ki to the minus 1 plus 1 tensor Fi plus something, but the something in the first tensor entry has exactly what I wanted to have. And so this is inside BC in the first tensor entry, and therefore the coideal property is satisfied. Okay. Right, so that is the first question, the coideal property. The second question is the specialization. Okay, to simplify notation, I set curly H to be mx U0 theta. This is in a way the biggest Hopf subalgebra I find inside my coideal subalgebra. And we set A to be U minus times H. So this is not contained in the coideal subalgebra, but it is something like a parabolic subalgebra, only I've made the torus ever so slightly smaller. Yeah, there's here, this is not all of U0, there's a bit missing, but here I have the semi-simple bit and then I take U minus. So this is like a parabolic with a slightly smaller torus. Okay, and then we define a filtration. A filtration on BC by a degree function on the generators. So I set degree of Bi is equal to 1 if I not in X, and degree of anything in H is 0. And so this defines me a filtration on BC by saying, well, any polynomial in the generators is of filter degree n if in each monomial there are at most n Bi's occurring. Okay, so we can ask what's the associated gradient of this. And the point is this, that we always get a surjective algebra homomorphism phi from the associated graded onto A, which maps Bi in degree 1 to Fi, and it maps U to U. Okay, so I may want to check that this is well defined. So I look at degree n here. And so what do I have to check? I have to check that the 0 doesn't map to something which is non-zero. Well, so if I'm in filter degree in degree n and the element is 0, well, then this means that I can actually write this with fewer Bi. Now, the point is that any representative I choose, I can look at it in the triangular decomposition of UQ of G. I can bring all the F's to the left. And where does it map to? Well, it maps to exactly those F's up to maybe a factors in H. Yeah, the point now that this element actually lies in lower filter degree means that I can write this with fewer F's. But then this means that the F's which I had at maximal degree actually must be 0 due to the Serre relations. Yeah, so this map is well defined. And then I need one more bit of notation. I tau is a set of representatives of tau orbits in I. Okay, so yeah, so I take these two, say, and so then we have the following theorem, which is already in the work of Letzter in the finite case, and which says that the following are equivalent. So the good situation where my specialization holds is this situation where this, so this is a surjective, always surjective algebra homomorphism. Yeah, but it needn't be injective if I choose the C to be the wrong values. Now, the good situation are those where phi is an isomorphism. Okay, so now this is equivalent to all sorts of other nice things. So we have a triangular decomposition of UQ of G. Yeah, so I can take A. Now A, I said, is essentially a parabolic. There's only a little bit missing. So let's put the little bit back in. Let's take KQ, the subalgebra generated by the KI to the plus minus 1 for I and IT, I tau. So these were the tau orbits. This subalgebra gives me exactly the elements which are missing to making this the whole parabolic. So this is the positive parabolic or negative parabolic corresponding to X. And then if I tensor this with Rx plus, so that's the nil radical, the positive nil radical for this parabolic, well, then this is everything. So this map is the multiplication map from the left to the right is an isomorphism. Now, if this phi is an isomorphism from the graded of BC to A, then it is not hard to believe that this will stay true if I replace this A by the BC. Yeah, essentially, I have the leading terms, I have everything in A. I may get some lower order terms, but the lower order terms will be either in here or already in BC.
Sorry. Maybe I think you made some missing about the letter K suffix. I don't know. KI, KJ, QKJ, large K. But some K, that's K. What is that K?
Okay, yes. Everything is correct, but it's not written well. So this is a bracket.
Okay, guys. I'm sorry.
This is a bracket.
I'm sorry.
Okay, yes, sorry about that. And this is my field. Okay, so second property is multiplication. From here to there is an isomorphism. Okay, third property. Well, UQG is a free left BC module. Well, if I have 2, then certainly 3 will hold. Yeah, but this is a very nice situation if you have a Hopf algebra, a pointed Hopf algebra, so the co-radical, the sum of the simple sub-co-algebras, the simple sub-co-algebras of this are all one-dimensional. So this is a pointed Hopf algebra. If you have a pointed Hopf algebra and a co-ideal subalgebra, then to be free is the same as to be faithfully flat over the co-ideal subalgebra. And these Hopf algebras with faithfully flat co-ideal subalgebras are commonly called quantum homogeneous spaces. And this is a very nice class of co-ideal subalgebras. And in the pointed case, this is also equivalent to the intersection of the co-ideal subalgebra with the co-radical, so with all the subalgebras generated by the KIs, to be a Hopf algebra itself. Yeah, so that means if some monomial in the KIs is in BC, then its inverse must also be in BC. That is what this condition says. So then there's a fourth condition, which is purely numerical. We want that Ci is equal to C tau of I if alpha I Wx alpha tau of I is equal to 0. Now, if I is tau of I, then this condition is empty. So this is for all I not in X. If I is tau of I, then this condition is empty. But if I is not tau of I, then one can actually check that this can only happen if Wx of alpha tau of I is just alpha tau of I. So then this becomes alpha I alpha tau of I. This means in particular that the alpha i's don't have any, so the corresponding white dots in the Satake diagram are not connected to any black dots. Well, then this means that if this condition here holds, then actually the BI is of the form Fi minus Ci. There's no TWX, there's just the E tau of I, Ki to the minus 1. And similarly, the B tau of I is equal to F tau of I minus C tau of I, EI, K tau of I to the minus 1. Okay, now you take these two elements and write down their commutator. If this is 0 and you can forget about the Wx, then the F's commute with each other, the E's commute with each other. So you only get the mixed terms. Yeah, you get an Fi with an EI, and you get an E tau of I with an F tau of I. Now, we know the relations, but the point is that if the C tau of I and the Ci are not the same, then there will be terms of the form Ki to the minus 1, K tau of I to the minus 1, which survive. And these terms would fall into your co-ideal subalgebra. And that is too big because you don't want terms of this form. Yeah, I mean, in the classical limit, if you write something like this, minus 1 divided by q minus 1, and you let the q go to 1, then this produces elements in the Cartan subalgebra which are not in K. Yeah, so that means if you don't have this condition, then the thing will not specialize to the right thing. But if it does, so that would be condition 5. Well, under suitable assumptions on the Ci, so we need, as before, that if we let the q go to 1 in the Ci, they need to specialize to the right numbers, essentially 1 up to our fudge factor. So if that holds, then this fourth condition is equivalent to BC going to U of k for Q going to 1. Okay. Right. So from now on, we always assume that these equivalent conditions 1 to 4 all hold. And that is the class of coideal subalgebras we want to work with. And so then there's only one last comment to make in this fundamental algebraic overview. And that is that we can now write our algebra in terms of generators and relations. So we have generators and relations for BC. We need the quantum Serre polynomial. So Sij of xy is the quantum Serre polynomial. L equals 0 to 1 minus Aij minus 1 to the L, 1 minus Aij. This is a Q binomial coefficient. Qi x to the 1 minus Aij minus L, y x to the L. And then the theorem due to Gay-Letzter in the finite case O2 maybe is the following. So we can look as BC over as an algebra over this maximal Hopf subalgebra. So BC is generated over this Hopf subalgebra H by the elements Bi. Okay, I need a little bit of notation. I want maybe put a plus here, and I want to define Bi is equal to Fi if I is an X. So then I have these for all I and I, subject only to the following relations. So we have K mu Bi is equal to Q to the minus alpha I mu Ei K mu. So for mu in Q theta, we have Ei Bj, the commutator. Well, this only gives us something if the j is in x and equal to the I. So it's delta ij ki minus ki to the minus 1 divided by qi minus qi to the minus 1. And then finally, we have some Serre type relations. So Sij of Bi Bj is equal to something. So now the point is, if I plug the Bi and the Bj in there and they are both not in X, then this has total degree 1 minus Aij plus 1. So this has a degree 2 minus Aij. If the Bj is in X, then it has degree 1 minus Aij. filter degree. And the point is that there is such an element such that for some Cij in filter degree minus Aij of BC. Okay, these lower order terms can be determined, but that is a hard question. So I think I have 5 seconds left. I better shut up. Right, thank you very much.
Is there questions? Is there questions? Oh, okay.
So you said that X needs to be finite type. So are there examples of co-ideal subalgebras coming from affine types?
Yes, there are plenty. So there is the simplest example is of type affine SL2. And you take X to be the empty set, and then you get the corresponding co-ideal is the Q1 Saga algebra. So that's the very simplest affine example, which has been investigated a lot. But in general, you can take any symmetrizable Kac-Moody and you get a host of these co-ideal subalgebras. There are certain generalized intersection GIM algebras, which were studied by some people, and they actually turned out to be co-ideal subalgebras of this letzter sense, the quantum GIM algebras, co-ideal quantum symmetric pair co-ideal subalgebras with respect to some involutions.
Okay, thank you.
Is there other questions? Okay, if not, thank you very much. Thank you. The morning session is all finished.